Well, we got those important mathematical ideas out of the way there. Um, so let's take a look at with a regular simple harmonic oscillator. All right. Um, and so the guy in the video I showed you, I can't remember his name. Anyway, he showed you some of this. We're going to go just a little bit further. I'm going to talk about it just a little bit more. So where do you see decay? Well, you see it in lots of places. I mean, everywhere you've got a vibration, the thing is going to decay unless something is constantly putting some energy into it. Okay, so decay is the mechanism at which the energy bleeds out into the environment. All right. Shock absorbers in your car are good. They're going to bleed out some of that vibrational energy. Otherwise, every time you hit a pothole or a rock in the road, your car would just start bouncing up and down like this. And very quickly, everybody would get motion sick. Then it would be messy. Actuators with feedback. Okay, so these are control systems. And yeah, I'm not sure why I put that example on there. Mechanical resonance, we've talked about that. Nuclear resonance is like when they stick you in an MRI machine, if you've ever had an MRI done, all right, there's a really strong magnetic field in there, and that causes your nuclei to kind of rotate like this, okay? And it's called precession, all right? And then they make sudden changes, boom, to that magnetic field, and that makes the little nuclei go zing. And then they slow down, and then they hit it again and go zing, and then it slows down. And so it goes from this really energetic oscillation state, and then it gradually calms down. And they actually measured that rate of calming down, because when the nucleus does that, it gives off a radio signal, and that's what they measure, and that's how they take a picture of your insides. Okay, this is really fascinating, and hopefully we'll get a chance to talk about that some more towards the end of the semester. Okay, so in the video, he correctly talked about these categories. Okay, so an overdamped system and a critically damped system, and the one that's not labeled on here is the underdamped system. Okay. Now, these are goofy names. All right. I didn't come up with these names. The names have to do with what's happening under the hood mathematically. Okay. In order to really solve this and build a good model mathematically, you have to use differential equations. All right. And many of you are in that class this semester right now, and you'll cover some of this. All right, you end up building what's called a second order linear homogeneous differential equation. And in this particular case, then when you solve for the answer, there's three categories of answer. Okay. And so the first category is this underdamped, where it's going to oscillate and gradually get slower and slower and slower. And that's what we see, where it comes down and up and down and up and like that. Okay. That's underdamped. Okay. Which makes it sound like, oh, there's not enough damping. But no, unfortunately, it's just a poor label. Okay. Then there is overdamped. Okay. And overdamped, that's this one where it's like, okay. And overdamped, there's no oscillation at all. Okay. And yeah, it behaves kind of oddly. It's not really an exponential decay. Okay. It's very unusual. So it's kind of its own thing. It's its own function, to be real honest. Okay. However, this one right here called critical damping. Okay, that is just a pure, straight out exponential decay. And what happens in critical damping is this whole term here is just equal to 1. Okay, and so you get, all you have left is that exponential decay term. Okay, like that. Okay, now let me get rid of some of this other stuff here. Boom, boom. Got too much pink on there. Okay. Now, if we take our peak here, 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 and the next one would be like over here somewhere. If we connect those things, okay, we have this. Okay, that's it. That's our, remember the first video, that's our envelope. Okay, so that's where the amplitude is becoming smaller. So we have an amplitude change part, and then we have the oscillation part right here. Okay, just like that. Now, that decay there, the decay constant gamma, that depends on several things. It depends on what we call the damping constant, I guess we might say. But this is the decay constant, so that's different. Okay, be careful. And the mass. All right, and so gamma is equal to B. All right, which has to do with the resistance to motion of the object, B divided by 2m. Okay, just like that. And one of the videos I'm going to do for you is going to be an example where I show you how we calculate some of that kind of stuff. Okay, so we're just kind of sticking with theories and ideas for the moment, but we'll slap some numbers on there for you later on. Okay. Okay. So let me write that back down again. And again, my program didn't translate very well for some reason. Okay. So the gamma is B over 2m. Okay. So if we've got a spring and a mass, okay, there's a certain spring constant K, a certain mass M. Okay, this thing's going to go up or down. Okay, and we can describe F equals MA as minus KX. Okay, now we've talked about that. All right, and that's how we get our oscillation. But where does the damping come in? Where does that come in? Well, that would come in if we start to take into account something like air resistance. All right. So as this thing is moving back and forth, the motion of the air has to get out of the way, and that creates a sort of a friction, okay, which fights the motion. And so we have this term here minus BV, okay, and that comes down to aerodynamics stuff there. So that's our coefficient of resistance for the velocity there. And up here in our equation, that B is the same. Okay. All right. And anyway, F equals MA. If we divide through by the mass, okay, we're going to end up with saying that A is minus K over M. We've seen that before. Minus B over M onto V. Okay, and again, this is the part that's going to lead us to gamma. Now, gamma, it's got that extra 2 in there, so be a little careful there. Don't forget the 2. Gamma is B over 2M, and it would take us 20 minutes to talk about why the 2 is there, so let's just go with it, and it doesn't really matter for us right now. Let's just say that it's there, okay? But that's where that part comes from, okay? All right. Yeah, good. Okay. All right, so I'm going to end this video here. So this is the end of part 2, and we'll do a couple more videos.